friends and physics loving people. I'm back with another video, this time on uncertainty principle and some of its applications. In this video I'll prove the uncertainty principle in terms of an experiment, and then we'll show you some of the applications. So let's proceed. So this is a famous experiment known as gamma ray microscope experiment, where we'll prove the Heisenberg uncertainty principle. In this particular experiment, we see a microscope is here, and this is where we find an electron, and a photon is striking the electron to see it. So a photon is used to find out an electron within a microscope. Now while discussing the resolution of between 2 points, the thing is that a microscope cannot resolve 2 points if the distance between them is less than or equal to this particular distance, where lambda is some wavelength of the light used, and then theta is the angular aperture of the microscope. So this condition must be avoided in order to resolve 2 points while observing through a microscope. So in the sense that it leads to some uncertainty, and while looking at an electron by using a microscope with the help of photon, there remains an uncertainty, and then uncertainty is simply this particular inequality, and this is equal to lambda by 2 sin theta. So del x represents the positional uncertainty, and it is given by equation 1, which is coming from the resolving power of a microscope. And as from equation 1, it's clear that where lambda is small and the uncertainty is small, and in that sense it is better to use the light of shortest wavelength in order to have least uncertainty. So lesser the wavelength, lesser the uncertainty, and that means the greater accuracy in determining the position of the electron while using a photon through a microscope. But another thing is that there is some compton recoiling of the electron, and where that will affect the wavelength, and the recoil order of the recoil is h nu by c, where nu is the frequency of the radiation, and then while the photon would enter will enter the microscope within an angle twice t, in that sense that there will be some uncertainty in momentum which will be perpendicular to the microscope, and this will be given by this particular thing h nu sin theta by c, and if theta is very small, then we sin theta is equal to 3, and it will be h theta by lambda for momentum uncertainty as given by equation 2. So we have two uncertainties in equation 1 due to resolving power of a microscope, and another due to compton recoiling given by equation 2. While entering the when the photon enters the microscope through an angle twice theta to see the electron. So the multiplication of equation 1 and 2 lead us to the equation 3, which is nothing but the Heisenberg's position momentum uncertainty principle. Thus we prove the principle, and certainly we were left with a very important question, that why don't we feel the effect of uncertainty principle in our daily life, even if you experimentally prove the relation with a gamma ray microscope experiment? The answer to this question is that the value of Planck constant is very small. For example, if you take a mass of 10 to the minus 5 gram, the position can be determined within an accuracy of 10 to the minus 5 centimeter, and then with the uncertainty principle, the velocity, it cannot be determined better than this accuracy 6 into 10 to the minus 17 centimeter per second, where m is the mass 10 to the minus 5, and using those particular relations for momentum m into v, where m is mass and p is some kind of v is velocity of the particle. So certainly this means that this velocity is not being precisely measurable, or quite undetermined regarding our daily life things, and in that case we cannot have uncertainty principle in our daily life. But had the value of h being larger, then definitely that uncertainty principle will have worked in our daily life. So small h is small, the Planck's constant is small, and that's why you don't see uncertainty principle in our daily life. That's the answer. Now, regarding one in particular important implication of the principle, we can discuss about the particle trajectory, where we see that in classical mechanics we usually discuss a particle in terms of its trajectory, and also the simultaneous measurement of position and momentum is possible there, because in the classical case we see the position as a function of time, and we take the time evolution of the position, and with this the time evolution of the position give us some trajectory, and that trajectory ultimately gives us position and momentum. And since both the position and momentum can be determined from the trajectory, it means that simultaneous measurement of position and momentum in case of classical world is possible, and it's only because the trajectory is possible in case of particle in a classical world. While in quantum mechanics, the time evolution of the particle is not in terms of some trajectory, it's in terms of some wave function, and we always talk about probability. So since probability is not a deterministic thing that we can definitely determine, so definitely there is some uncertainty in momentum and as well as position, and so discussing the matter wave, which is representing a particle, we can say that a wave cannot be located in space, and this means that there is some positional uncertainty or the spread in location. And also, while locating the particle, we need a detector, and there is always exchange of momentum while using the detector to locate it. And in that sense also, we had some exchange of momentum, and this exchange of momentum ultimately leads to uncertainty in momentum also. So while discussing in terms of quantum mechanical point of view, we talk about matter waves. While we talk about matter waves, the particle cannot be located in space, leading to some spread or uncertainty in it, and at the same time, while using a detector, we are left with some uncertainty in momentum. So we're thus left with both in positional uncertainty and as well as momentum uncertainty regarding a quantum mechanical particle. So when these uncertainties are there, the particle trajectories are not determinable, or we can say that its positions are unpredictable, as we are now with some kinds of probability for its position in terms of wave functions. So the concept of trajectory goes away, which is an important thing in classical physics. So in classical physics, we have trajectory, but in quantum mechanics, this concept of trajectory goes, and we are only with Heisenberg uncertainty principle. So let's now turn into some applications of uncertainty principle. We'll discuss these things. The first one is binding energy of each atom. We see here that the energy of atom is given by equation 1, where P is momentum, M is mass, and this is the potential energy part. Now this, if R is small, then definitely this part is large, potential energy is large, and this means that for small r, the uncertainty position is also small. Since positional uncertainty is small, this means that momentum uncertainty is large, and that means this p square by twice m is also large, because kinetic energy is associated with p square by twice m. Now since kinetic energy is large, this means that that E will be that kinetic energy is more, means that kinetic energy is a positive term. That means that E is now becoming positive. It may become positive due to this increase in P. And if on the other hand, if make that kinetic energy we make the kinetic energy small by making this P small, that means the uncertainty in momentum is small. In that case, that R will be large, and since R is large, that means that uncertainty in position will also be large. So we are now left with more value in kinetic energy for less R, and more potential energy for large momentum. So this means that for one case, for a small positional uncertainty, we have the chance of E becoming positive, and for more P, we have that this positional uncertainty becoming large, and in that case also we have some kind of kinetic energy becoming small and this E becoming negative in that sense. So we are within some extreme cases, and which will lead to the system unstable. So there must be some particular value of R where that E maintains the stability condition in terms of equation 1. So let's talk about the second application of it, that is the non-existence of electron within the nucleus. Initially it was believed that electron can exist within the nucleus, but however with the application of uncertainty principle, it was proved that an electron cannot be a part of the nucleus. We usually know that the nucleus has a radius of 1 Fermi, about 10 to the minus 14 meter, and in a sense then uncertainty in a momentum will be this one is crossed by R naught, and if this is the uncertainty, then definitely the momentum must be of this at least this order, because the minimum value of the momentum is always at least equal to the uncertainty in it. So H crossed by R naught is the uncertainty momentum, and also it is the lowest value of the momentum. So P is equal to H crossed by R naught, and so the minimum kinetic energy, which would be now when calculated with this relation, H cross square twice M naught R naught square, would give us 20 MeV. And then experimentally it was found that the electron coming out of a nucleus have an energy hardly of 4 MeV, and this means that the calculation of this theoretical energy of 20 MeV definitely shows that electron cannot be a part of that nucleus. So the Heisenberg uncertainty principle not only talks about the bounding system of a hydrogen atom, it also talks about the non-existence of electron within the nucleus. So let's go for the third one. This is how the strength of the nuclear force can be determined with the help of Heisenberg uncertainty principle. Again we see that the proton within a nucleus is within this 10 to the minus 15 meter or 10 to the minus 13 centimeter. So uncertainty again is like this, and the kinetic energy having a mass of this 1.6 into 10 to the minus 24 gram for a proton can be calculated out to be this. It is also equal to 20 MeV. Since the proton is a bound within the bound kind of particle with a nucleus, the average potential energy must be negative and has a greater value of this one. But and this proves actually that nuclear force can have can act within a radius of this, and also that the potential energy related to a proton must be having a magnitude greater than 20 MeV. And going back to the fourth one, that we can calculate the radius or estimate the radius of Bohr's first orbit using the Heisenberg uncertainty principle. So again we using this relation, if del P equal to H cross by del X, the uncertainty principle, the uncertainty momentum is del P square by twice M naught, and so this is equal to equation 2. And uncertainty and potential energy, which Z equal to 1, is this, because we know the expression for potential energy, E square by twice E square by 4 pi epsilon naught R. Since R is equal to del X here, we can we're calculating uncertainty in potential energy, so we're putting instead of R it del X, the uncertainty in position. So del D represents uncertainty in kinetic energy, del V represents uncertainty in potential energy. So uncertainty in total energy is the plus del T plus del V, and is equal to this given by equation 4. And uncertainty will be momentum, will be minimum when this is equal to 0, and this condition is from the conception of differentiation. So from equation 4, we doing all this differentiation, we find del X equal to this given by equation 6, and the double differentiation of this will lead us to this equation. This is very simple differentiation, and ultimately we are having double differentiation equal to this given by equation 7. Now this is definitely positive quantity because E square and all these things are positive. So the condition that minimum of the energy uncertainty in energy is minimum if these conditions are satisfied are now given by equation 6 and 7 respectively. And since equation 6 gives us the condition of minimum in the first orbit, so the radius of the first orbit is determined using this equation, that is del x equal to r minimum, and already del x is given by equation 6 here. Del x is given by equation 6 here. Putting all these values here, that our minimum value of Bohr radius is a square epsilon naught pi m naught e square, and certainly this is what we usually calculate in atomic physics or while discussing the Bohr atomic conditions in quantum mechanics. So this is Bohr's first orbit. If you put all these values, this is equal to 5.3 into 10 to the minus 11 meter. So Heisenberg uncertainty principle is another thing that can help us to determine the Bohr's first orbit. Now regarding the fifth application, that is virtual particles and range of interactions. So we can find out how that different kind of forces, whether it is strong or electromagnetic forces, the range of the intermediate particle, that we can determine using this Heisenberg uncertainty principle. For example, we take this one, that a boson acting as a mediator particle having mass mx and lifetime tx, the range is equal to r equal to c into tx. Usually we take the intermediate particle moving with the speed of light, that's why it is c into tx. So this is its range, and now using the energy time and uncertainty principle, this is equal to a squared by 2, and as we know, since this del is nothing is the rest mass energy, so rest mass energy of the boson is equal to del equal to m naught mx c square. So using all this here, we can find that del t equal to a squared by twice mx c square, and the range is thus equal to, just putting the value of del t here, del t representing tx, we see that r is equal to a squared twice mx c, and using all these values, like in case of electromagnetic interaction where photon is the mediator particle, that mx is equal to 0, and if you put mx equal to 0, then its range is infinity. And similarly, in the case of strong interaction in strong nuclear force, this pi naught or pi plus minus are also mediator particles having all equal masses. If we take this as mediator particle, this pi meson, then we putting the mass of this pi meson, we find that this range is equal to 1 Fermi, and this is all our experimentally observed facts. Also regarding these virtual particles and range of interaction, you must remember that for every kind of forces there is always a mediating particle, and that mediating particle is photon for electromagnetic interaction, and and the bosons are for bosons like pions are for strong interactions. So there are 4 forces, as we know. For weak forces, W and Z bosons are responsible, and for gravitational interaction it is graviton. So all this in mediating particles are obeying Bose-Einstein statistics, and that's why they are known as bosons, and that's why we're calculating the mediating particle as a boson here. So with all this, we see that uncertainty principle has a large number of applications. We prove all these things here, from stability of an atom to non-existence of electrons, and then to range of nuclear forces or different kind of forces using the concept of mediating particles. There we are ultimately left in some assessment here. Explain the gamma ray microscope experiment, how the uncertainty principle can be proved, and whether trajectory is possible for a quantum mechanical particle, unlike in case of classical version, and then some applications of the Heisenberg uncertainty principle. With all this, I'm ending up this video. Keep watching, and also don't forget to comment on our videos. Thank you very much for watching once again.